Chapter 2.2, Limits and how to use the delta epsilon proof. Now, the delta epsilon proof is often found to be difficult to understand and difficult to apply. But what you end up doing is doing inequality proofs, okay? You're always driving towards the inequality. Now, remember that while this seems quite difficult, this is actually just a demonstration step to show you how the delta epsilon concept works. Once we get past this, we will develop systematic theorems on how to handle the derivatives and integrals, and stuff will be a lot easier, even if you find this part hard. So let's look at this example here. So let's say x squared limit of x squared as x approaches 0 is 0. Now that's quite obvious, but how do we use the delta epsilon proof? So what we're starting with, we are given by definition that x squared is less than epsilon. Okay, given epsilon, we have to figure out a way such that the value of x minus 0, since that's where it's going, is less than something of epsilon. Okay, that's a question mark. Some kind of form of epsilon. How do you do that? Well, let's take the square root. So if we take the square root, we have then absolute value of x is less than epsilon to the power 1/2 square root of epsilon, and we'll set that to be delta, and we're done. Because if absolute, that's what we're looking for. Okay, find absolute value of x is some form of epsilon in inequality. So as long as absolute value of x is less than delta, which is epsilon square root, then this relationship will hold, and we are finished. So they think, well, that sounds pretty good. Well, that is a super easy example. Look at this one. Now, this example is very similar to that one. That's x squared. This is x square root. So they should be equally easy, right? But it doesn't work out that way, because if you do this problem, okay, by definition, fx minus L, okay, so fx, by the definition of the delta epsilon proof, we have fx, which is square root of x, minus L, the limit, which is square root of a. This is given as less than epsilon. We have to somehow show the x minus a, okay, the x itself has to be less than some kind of function of epsilon. We have to derive from here to here. Now, how do you derive a relationship from here to here? It's not obvious at first. So eventually, we end up messing around, playing with tricks, and doing stuff, hoping that this will show up one way or the other. So what we're going to do is we will do what we normally do with this kind of thing. Now, in algebra, whenever you have this kind of stuff, you are told to multiply it by something like this. There's a name for it. I can't remember what it's called, but whatever. The point is you have to do this and naturalization or rationalization or something. Anyway, we often do this in algebra, okay? So once you do this, we'll just multiply this and see where it gets us. So so the good thing is the top becomes, multiplied together becomes x minus a. That's what we're looking for. However, there's also this thing left, okay? Plus square root of a. So we got this. Now the top looks like what we're driving for, because we're driving for this thing. But what about that? That is still there. So we're going to now pull a trick that says, well, if we reduce the denominator, so we have just x minus a and square root of a. Remember, a is a constant, okay? So this is going to be true. The reason is because we got rid of square root of x. So now the denominator is smaller, which means the whole fraction is going to be bigger. All right. So now we have x minus a divided by a constant. We will put this to be we'll put this to be epsilon. Okay, which means that x minus a has to be less than epsilon square root of a times epsilon. And we'll set that equal to delta. And then we're done. Now, in this particular problem, you have to mind a certain minor detail, and the detail being that you have, say you have a here, okay? and you have 0 here. And being that we're working with a square root, that everything has to be positive. So you have to make sure that your delta neighborhood, okay, this length is delta, your delta neighborhood has to stay positive, which means that a minus delta has to be bigger than 0. Okay, otherwise nothing makes sense. So that's the other condition. So delta has to be this, and a minus delta has to be bigger than 0, or delta has to be less than 8. That's just a small detail, but that's mainly what we get. Is we'll set delta to be square root of a times epsilon, and we do that, this relationship will hold. So that's the second proof. As you can see, we have to pull a bunch of tricks to just do something, well, that obvious. Now the next thing we're going to do is equally obvious, and we still have to pull some fancy trick to get it through. That is, we must prove the sine x as x approach 0 is 0. Well, that's pretty obvious. Of course it's 0. But to prove it, here's what we're driving at. So by the delta epsilon definition, so we must prove sine x minus 0 has to be, that's the limit, less than epsilon, okay, that's given. We have to show x is less than some kind of a relationship of epsilon. Now, how do you drive from sine x to x? Do you take the inverse sine or something? Well, that wouldn't make it any easier, but so after much struggling, you try to do a geometric proof. Now that is a circle, and it's a circle with unit value with radius 1. And this is our x. Remember, x is close to 0 when we're going to 0, so we can draw x like this. It makes sense. And we'll drop a perpendicular line right here. This is perpendicular. And we'll also connect these 2 points. We'll call this thing D and call this thing A. Okay, this is the origin, of course. We're not even going to write down the origin. That's a waste of time. Anyway, so that's the origin. And so this is 1, okay? And from geometry or wherever this is taught, you remember that if the angle is x and the radius is 1, this arc length is also x. This thing here, from D bent its way to A, is also x. So then here's how we prove this. We'll prove this thing completely relying on geometry, which says that, so then sine, remember, we're driving from sine x to x, okay? So sine of x, which is what? Which is this distance right here, okay? No, this is cosine, sorry. This is cosine of x, this length, this height here is sine x. Okay, we'll use cosine for this one. So anyway, sine of x, which is this length here, is going to be less than or equal to dA. That's by the Pythagoras theorem, that the leg of a right angle triangle has to be always shorter than the hypotenuse, which is less than or equal to x, the curve here. And why is that? Is because that's because of a theorem in geometry that the chord of a circle is going to be not as long as the part of the arc itself. And you have to remember all that stuff from geometry, but it's also intuitively obvious. So sine x is less than x, so we'll set this thing to be, if this is epsilon, which we'll set delta as delta, because we have sine x, which is less than epsilon, but it also happens to be less than x, which is very nice. So if delta and epsilon is the same, as long as x is less than delta, sine x is less than epsilon, as we have shown in the step. Now the cosine is shown in a very similar way. Now to show the cosine, we have the function cosine x minus the limit, which is 1. Okay. Now what is that? This will do exactly the same, which says this is cosine x right here. So, and this whole thing is 1. Okay. So this thing right here is cosine x minus 1. This, which again is less than or equal to the hypotenuse here in this right angle triangle, in this particular triangle, which is again less than or equal to the curve. The chord is less than or equal to the curve. which we will again set it to be epsilon and set it as delta. And at this point, then the same principle applies. As long as x is less than delta, cosine x minus 1 is less than epsilon, because cosine x minus 1 is actually less than x itself. So that comes out to be quite a neat proof, even though it depends heavily on geometry. Eventually, after this section, we're going to get past this stuff and probably won't touch it for a long time and do derivatives and integrals, which will be much easier and far more systematic. But for now, you have to rack your brains and figure out a trick like this. The best way to just to memorize it, the different ways to do a few examples.